So we looked at using the quadratic when we have information of the form. If we can rearrange our math in our equilibrium information into this format, a equals x squared plus bx plus c, we can use the quadratic equation. Of course, this is a long, drawn-out process. The problem is these squared terms. Whenever we have these squared terms in our algebra, we end up with this difficulty. You can't just solve for x. You have to massage the data, and so this can be time-consuming. Luckily for us, there are a number of shortcuts that add what I like to call finesse to the equilibrium statements. And so a couple of the shortcuts that we're going to talk about, the perfect square is probably the simplest. So really it is this square term that we care about. And so we're going to take a look at one of the easiest way to get rid of this square term, and that is using a perfect square. If you're lucky and your math is set up right, oftentimes in lab you can control this, you end up with what's called a perfect square, and you can solve the equation quite trivially. So let's take a look at a situation where we have the following: 2HCl gas in equilibrium with H2 plus Cl2. We know that at equilibrium, the partial pressure of the HCl at equilibrium will equal the initial partial pressure minus whatever is consumed in the reaction, in this case 2x. And along those same lines, the partial pressure of the H2 will be whatever is gained in the reaction, in this case plus x. The initial value plus whatever is gained. And we can write a similar statement for the chlorine, because these concentration values are not independent of one another. They are all related via stoichiometry. So we can relate this to the equilibrium statement, Kp. We know that the equilibrium pressure will have the following form of the equilibrium constant: PHCl squared. And if we know each of these values, we can plug them in and solve. But we don't know what they are at equilibrium. We only know what they are before equilibrium. Before equilibrium, we know that the initial concentration of pH2 will equal that of the PCl2, which will be equal to 0.300 atmospheres. And that the partial pressure of the HCl will equal 0.500 atmospheres. Now, once we know this, we can then wait for the system to come to equilibrium, and that's where these values come in. We know these initial values, and we can relate them to the values at equilibrium and combine them with this equation. So let's see what that actually looks like. Well, we know that the Kp in this case will equal 0.255. And so we can write 0.255 is equal to the pressure, the partial pressure of the H2 initial, plus x, partial pressure of the Cl2 plus x, all divided by the partial pressure of the HCl initial minus 2x, all of that squared. Now, we could run this through the quadratic, but as we saw yesterday, that takes some time. All right, and so it can be done, but it's not very elegant. Instead, we can use a little trick of math. Notice that this becomes equal to 0.300 when we actually plug in the numbers plus x. This actually becomes equal to 0.300 plus x, and times 0.300 plus x. Again, just plugging in our values from our starting conditions. All this divided by 0.500 ATM minus 2x squared. And if you have a mathematical eye, what you'll see is that this can be rewritten as 0.300 plus x squared, because these two quantities are in fact the same. All of that divided by 0.500 ATM plus 2x squared equal to 0.255. Now what this means is that, well, these are just two square terms, and we can eliminate this taking the square root of both sides, y over z. So you can use this little trick. And solve the equation such that we take the square root of both sides of this equation to give us 0.505 equal to 0.300 plus x divided by 0.500 is 2x. Now, we're left with one equation and one unknown, and all we have to do is rearrange. Again, if you're familiar with the algebra, you can skip ahead a little. Well, time will be shown. And so let's just actually just do the rearrangement. We get the following. 0.500 minus 2x times 0.505, dropping the units, is equal to 0.300 plus x. Multiply out the terms, and you get 0.252 minus 1.01x is equal to 0.300 plus x. You then combine terms respectively. This becomes 0.252 minus 0.300 equal 1.01x plus x, which combine together to produce 2.01x is equal to negative 0.048. X will become equal to 0.0238. X is equal to negative 2.38. Right? So the temptation here is to stop, and go, yay, this is the answer, But that's not the case. No. X is just the change represented by the course of the reaction. So the real work is coming in and plugging this back into our starting conditions, which says that the partial pressure at equilibrium will equal the partial pressure initial minus x. And we'll do the same thing for the hydrogen minus X. Sorry, in this case, plus X. Partial pressure plus X. And the partial pressure of the HCl initial plus minus 2x. Those will be those values. So we plug those in. This will become equal to 0.300 plus x, which would be, in this case, x would be negative 0.0238. This will give us the partial pressure of the Cl2, which in this case is also equal to the partial pressure of the hydrogen at equilibrium, 0.276 atmospheres. And we can do the same thing for the HCl to give us a value of 0.548 atmospheres. Now we should be able to check our values. Again, we can plug these back into our equilibrium statement. 0.276 for the partial pressure of each, 0.276, all divided by the partial pressure, 0.548. ATMs, squared should give us a value equivalent to our equilibrium constant. Which I get is equal to 0.254 as a value, which compares reasonably well to our equilibrium concentration. So we've checked our answer, and we can see that it gives us a value very close to our starting condition. Yay. All right, so perfect squares. In those situations when you can eliminate based upon a perfect square. Anytime you can just simply take a square term, it works very well. Higher orders work as well, cube terms and more, though those are far rarer. But they do help simplify the math greatly.